just trying to start a conversation.
Oh, great. I mean, this is so important in forensics, and I just wanted to have your opinion on on this. I mean, yeah. I think it's really great that you started to work on this.
Awesome. Thank you very much again, Serge, for this amazing presentation. We're going to be moving to our next keynote speaker, Justus Thies, who is an independent research group leader at the Max Planck Institute for Intelligent Systems. He's well known for his research with an intersection of graphics, computer vision, and machine learning. And he's been before working at the TUM in Munich. And please, Justus, the floor is yours.
Thanks a lot. I hope you can hear me and see my screen. Okay. So thanks a lot for the introduction and for having me here. So I recently joined the Max Planck Institute for Intelligent Systems, and my group is basically called as the same like the title of the talk. So it's Neural Capture and Synthesis. And so in this workshop, you will have plenty of talks that will cover detection of deepfakes and also manipulated media. And I actually want to focus more on the counterpart, the creation of synthetic media. And I guess a lot of my work is already known, and it's a lot about faces, bodies, and how we can track faces and bodies. And I guess the most prominent work of mine is this real-time facial reenactment, which is already quite old. It's like 5 years old, but it's still like one of the most famous manipulation methods that is out there. And it also shares the core components that we also use in more advanced techniques. So behind this real-time facial reenactment, we basically have these components that we need to reconstruct the motions of this source actor, and we also have to reconstruct the target actor in some way. And then we transfer the motions from the source to the target, and then we composite it with an original image or video. And in the end, you will get a result that looks like this, where you, like a human, has a difficult time to see that it's an actual fake. And we did this here in a real-time setup where we transferred motions from one person to another. But of course, you can also do this with recorded videos that you find on the internet. And you can transfer, for example, a speech from Trump to Obama. And I think that's basically the critical part why we actually have like this workshop. And if you have a look at all the comments on YouTube about these techniques that we show there, you will see that a lot of people are actually amazed by the technology, but a lot of people are also scared, and they are kind of terrified by the implications, and often also ask the question if this is actually a legal thing, what we are doing here. And especially like if you, for example, get an email where people say that your inventions are similar to the invention of an atomic bomb, you should think about what, or is it actually something that you want to work on? And so the basic question is, why do we invent such technology? And what is our intent? And does synthetic media has any benefits? And I think we can say that it has a lot of positive and like really good benefits. And I want to talk about these in the couple of minutes. So I think many people, or like most people already used some media manipulation tool, for example, to have like these bunny ears here or something like this. So you basically manipulate your photo and you share it typically on social media. We see a lot of like these beauty filters that are integrated in the camera apps. We have also like these animojis that create some synthetic media where you have some animoji here talking. And there are also a lot of other approaches or tools that, for example, generate these cartoon-like images from a real image. So there's also like a workshop here at CVPR, which is called Creative Computer Vision. I think that's also a quite interesting workshop that you might want to have a look at. Of course, beside this, I mean, this is basically consumer level fake generation. And on the other hand, we also have like the entire movie industry. And in the movie industry, you have a lot of use cases. And one is, for example, like this visual dubbing, where you want to translate a movie into a different language, and you want to make sure that the lip motions are in sync with the translated language. Of course, there are also, I mean, for this application, facial reenactment is basically the tool that you want to use. But of course, you can also, like these face swapping applications like deepfake, like the original deepfake application is a face swapping technique. And these could also be used in the movie industry. For example, if you have a stuntman and you want to replace the face of the stuntman with the actual actor. Besides the movie industry, we also have a big field for computer-generated content, where you have an AI, and this AI is, for example, a bot that communicates with a customer. So there we will see a lot of upcoming startups that will basically implement this, that you have basically a talking head that corresponds, or like you can basically have a conversation with an AI and you basically see the AI talking. So you have a visual feed there. There's also the entire, I mean, this conversational AI is already part of telecommunication, but we can also see other use cases in the field of telecommunication. For example, this enhancement and also eye gaze correction. If you want to talk to someone, you want to make sure that the eye gaze gazes towards the person you are talking to. Especially if you have a webcam, then you look typically somewhere to the side or so. And you can basically generate an image where you have the eye gaze corrected. And that's also some kind of fake, basically. When we talk about telecommunication, there's also this field of cameras or like built-in devices. For example, you have these smart glasses and you want to have conference with these smart glasses. Then you have the problem that you can, for example, mount a camera here on the side of the smart glasses, but then you get these distorted views. And typically you don't want to send over these distorted views here to your communication partner. And that's why we worked here on a project where we basically frontalize these images, and then you get these predictions where you can basically see the other person in a frontal view. But in general, I'm more interested in 3D content. So it's about basically digital humans in AR, VR. So we want to meet each other in AR or VR to be able to have collaborative working in VR. So we want to see each other. We want to show objects. We want to interact with these objects. And this area research basically has a lot of implications, social implications, about how and where we basically live. Because if this collaborative working in AR works at some point, you can basically do it remotely somewhere in the world. And this, of course, also has influence on, for example, the traffic is reduced and so on. And in this field, I already did a couple of works. These are only a few where we have like this face VR, where we virtually remove these VR goggles such that we can render a stereoscopic avatar of the person, such that we can communicate with the person here using a VR headset. We also have a lot of publications in the area of 4D facial avatar touch generation for faces, but also for bodies here. And I want to mention that this field is actually quite fast moving, and there are a lot of related works or works that try to do something similar. Like this area of digital humans is really fast growing. And I mean, just to name a couple of names that you might have seen in the couple of last weeks, there's Ganymede, Leap, Scale, SimplePix, Function 4D, and all of these methods that basically target to reconstruct and animate digital humans for the purpose of these VR applications. And this field is basically really fast moving, also because there's a really high push from the industry side. And we can actually see that every big company is having some research team around this digital humans problem, or like the goal to generate digital humans. And they all have, a lot of them have this telecommunication in mind to revolutionize this telecommunication in VR and AR. But of course, there are also other commercial applications that you can have in mind if we are talking about digital humans. For example, virtual mirrors, and this could, for example, be important for Amazon, that you can select different clothings and you see how it looks on your body. And there are also a lot of these fitness apps that track the body shape. And actually, all of these applications are somehow connected to the synthetic media and also to these deepfakes. And as I mentioned, it's for all of these applications, it's about the capturing part, like the capturing of the human shape, but also appearance, and then the synthesis part. And that's actually why my group is called Neural Capture and Synthesis, because I want to focus on both of these parts, the capturing of human motions and also the synthesis part. And my research is actually human-centric, so it's all about like these human faces, human bodies, but it's also about the reconstruction of human environments. So this telecommunication in VR, you also have to reconstruct or display some room where you basically meet. And if you want to talk about some object, you also want to like reconstruct this object. And there you have a lot of research in the area of non-rigid reconstruction to basically be able to reconstruct non-rigid moving objects that you can interact with. And I think that's a really, really big field here where you can do research. And all of these different parts, faces, bodies, and also scenes, they actually share a lot of commonalities. And it's a lot about these fields of neural rendering and this neural capturing. And I want to give a short overview of how these pipelines actually look like. And such a general pipeline, for example, for faces, looks something like this. So you have these two parts. You have the motion capturing part and you have the neural rendering part. The neural renderer basically has the target to generate your output. It could be an image, it could be a video, 2D or 3D content. And you have here the conditioning of the neural renderer, which basically tells you how the face should look like. And this is basically the motion capturing. And of course, you can have, like, once this neural renderer is trained, you can basically feed in other expressions here, for example. And so the goal is that you have a neural renderer here, which is giving you some controllability such that you can modify the image content here. And if we have a look at these components, they all differ from method to method. And just to name or to display some here is like for the motion capturing, there are different types of motion capturing that you can provide or that you estimate. So a lot of papers or works use sparse motion capturing data. So you detect sparse landmarks here. You can also have like these joint positions for a body. There are also methods, for example, like this deep video portraits, or also this face-to-face, which uses a dense tracking here. So you really reconstruct a 3D mesh, and you can have this for faces, for bodies, and you can also have really high quality 3D scans here. On the other hand, like these, this sparse and dense, they are kind of interpretable, and you can also have a network that basically gives you some kind of codec, which describes the state of the face. And given these inputs here, so these are basically the conditionings for the rendering part here. And this renderer takes these inputs, and it has some formulation of how to generate such an image. And when we talk about neural rendering actually means that we want to modify the classical rendering pipeline, or the concepts of classical rendering. And there are, for example, these like standard rasterization, or you have some kind of volumetric rendering, you have ray tracing or so. So this is how you can basically generate images. So there are approaches that use rasterization and insert some features, for example, here. And you can basically use the rasterizer to rasterize these inputs here. And you have learnable features that, for example, live on the surface here of this dense face mesh here. And you rasterize these features, which basically gives you an image here of features that then is interpreted by a neural network that then outputs this image here on the right. You can also have some kind of volumetric rendering here, as I mentioned. If you have something like this, you need to be able to sample along the ray, and you integrate basically some scene information, for example, color and density values. And in the end, you have like the integral gives you a pixel color. So this is about the neural rendering part. I will show later an example of that. And of course, if you have this general pipeline, the output is also important, like what you want to achieve in the end. And like classical deepfakes, they have a fixed view. And a lot of these more recent approaches, they go into the direction of novel view, because novel views are important for applications like virtual reality, teleconferencing. As I mentioned, I want to quickly go over a work that we will also present at CVPR this year. It's called Nerface, and Nerface basically gets a sequence of images as input, so a standard video here. And from this video, we want to generate a 4D avatar, which we can control. So we want to control the pose and also the expressions. And the idea is that we basically use some kind of classical rasterizer here, which basically shoots rays through pixels, and it basically evaluates a function at discrete steps here. And this function basically stores some scene information. And in this case, we store this, like the function basically gives us a color value and a density value. And based on these values, we can basically have a volumetric integration to get the color value for this pixel here. And this scene function, basically, which gives us these color and density values, that's represented as an MLP. So we have a scene representation network here, which outputs the color and density values. And based on that, you can basically shoot rays. You sample a lot of times here in this 3D volume, and you get these color and density values, and via this integration, you get the final pixel color here as output. And the overall pipeline looks like this. And here, again, you can see these parts here, that you have a motion capturing part, a neural rendering part, and this output layer. And we have here a classical face tracker running that basically gives us the pose and also expression parameters of the face. And then we learn basically a scene representation network, like this function that gives us density and color based on the pose and the expressions here. And once we have trained this, we can basically change pose and expression to generate different images. And that's something that we show here. So this is a comparison to other video generation tools. And as you can see, our approach basically gives a really 3D content stable result. So the head is not somehow distorted. It's really stable. So you don't have these distortions like from the old methods here. And of course, you can also use this for facial reenactment, which then looks like this here. So you just apply the expressions and pose from the source actor to this trained target actor here. As I mentioned, I'm like really focusing on all of these three parts. And if you are interested, there are a couple of more papers or works to explore, where we basically, for example, try to reconstruct the entire human body. That's here, like these dynamic surface function networks. We also have works about 3D reconstruction of scenes. And the interesting thing is that all of these methods here, they share some parts. For these, it's, for example, like the neural scene representation. So all of these basically use some kind of MLP, which give informations about the scene, density colors or offsets here, and in this case, sign distance fields. There are also upcoming tutorials in this field that I want to just highlight. The SIGGRAPH tutorial here is quite interesting because it covers a lot of the most recent works here. And there are also old state-of-the-art reports from last year, which are really kind of outdated because you have a lot of new work in this field. And with that, I want to thank you for your attention, and I'm happy to take questions.
Thank you, Justus. That was pretty impressive. Any question from the audience that we have today? Opening the floor.
Hi, Justus. I'll ask the first question again, if you don't mind. So you started off by telling us about some of the concerns that people have around this type of rendering, which is understandable. And I'm curious, how are you thinking about this? So, we've been seeing reports of things like non-consensual pornography being a real problem, particularly for women. So what do we as a community do to put the safeguards in place? I mean, obviously not working on it is not the answer. And so what do we do? Like, how do we approach the weaponization of this technology? Or how are you thinking about it, at least?
Yeah, I mean, the weaponization of this technology, I mean, that's a really big issue. And especially for individual persons, that's a really issue. Like, you have all this cyber mobbing going on. And I mean, if it's out there, the fake, then you can't revoke it, and everybody already has seen it. So it can create a lot of damage. And that's also one of the reasons why a lot of the work is not publicly available, like the source code. And I think it's really, I mean, it's about the spreading of these fakes. So I think social media has a lot of, like, the companies behind social media have a key role in this thing. They basically have to prevent, like, the spreading of such things. But of course, like, I mean, also the law enforcement at some point has to find the people that basically publish such fakes. And I think that's also kind of critical. And I mean, for the researchers, I think it's really difficult. I mean, they have to see that there are all of these possible use cases and malicious use cases. And they should also be careful with whom they want to share the code, especially if you just publish it on GitHub, such that everyone can use it and create some bot, a Telegram bot or something that basically generates these fakes. I think that's kind of a problem.
That's an interesting remark. Definitely, that could be more like security by obscurity by not sharing the code. I agree that we have to find mechanisms to make sure that your research is safe for
my point is not like hiding the code. It's about distributing the code.
Correct.
It's about the masses that can basically use the tools. I mean, it's kind of this democratization of these fake tools, and it's probably not the best idea to really, like, democratize these tools to everyone. So I mean, if school kids have these tools, they will use it, and of course there will be damage.
That's a good perspective, Justus. Thank you very much. And